We'll have Brad tell us, because I don't know. We have to ask Brad, actually. Ask Brad. I can load yours whenever. Load yours whenever. He's on board. My mouse and I are having a war here. What am I showing up there? This? Okay. Thank you. I keep losing this mouse. Why is my mouse not working?
It's not working.
Oh, my mouse and I are having a war. Yeah, I can use the mouse on here. That's fine. Yeah. Well, we're gonna test. He needs to get that on. Yeah.
And then go into the
Hey, this is Cindy. How are you? I'm good. Hang on just a second. I'm trying to. Are you guys ready to log in, or have you logged in again for the next one? Okay, can you see the slides at this point? Can you see a slide? Yay! Only half of the slide? Oh yeah, well it's because we're kind of mucking around with something here. Yeah. That's why I'm trying to get in here. I'm trying to do multiple things at once, which is causing me issues here. Okay, you should be good there. Okay, I'm going to hand you to Kevin for just a second.
Hi. So you're still seeing something?
Just a little bit when we're done with the meeting today.
Yeah, someone's missing this, or somebody got to make this. That's exactly what he's saying.
I did. Yeah, I did. So that's all he's getting. That probably hurt. And you got the slides flipper? Okay. Yeah. See if he's seeing the whole screen now.
It's
It's muted in the back. It's muted in the back. So.
What you're seeing now? So you've seen Sean Convery?
Yeah.
You see that name? Oh, he's showing you right now. He's not seeing.
No, because I stopped sharing.
Now you see everything? Okay. All right.
Whenever anyone from the audience makes a comment, it's one of those mirrors where they are, and whoever's on the line or through the computer can pick up that comment and see what the response is. So that's what they are. We're not recording you.
Is that
I want to, I have like multiple copies of this thing going. Okay, so we want this. Okay.
Oh, that's good.
What do you see now?
Meanwhile,
You see this one?
Is he seeing the slide or me?
Okay.
Is he seeing me or the slide?
I'm seeing the slides, but there's still 30, 60 seconds or whatever.
Okay.
So,
But he is seeing the slide.
yeah, audio's still going.
Okay, so today we're talking about sustainability and research, laboratory design, and operations. And I wanted to give a little history before I introduce our speakers. EPA launched sustainability efforts in 1996 with something called Project Excel. It was big in the New England region, focused on federal agency efforts with respect to RFRA, which is the resource. Now I've forgotten what it is.
Resource Conservation and Recovery Act.
I knew somebody did. In 1999, they expanded to include other public and private sectors and design processes for initial building at Anschutz was taking place about that same time. So it wasn't really part of what we were looking at because it was so new. In 1993, approximately at the same time, U.S. Green Building Council was established, and then they launched Leadership in Energy and Environmental Design.
No, it's not you.
Beginning
It's
in
the slide
2000, they
thing that
took
started me
on
insane.
multiple interrelated systems for all aspects of
It's not you.
development and construction in all sectors. Most recently, in 2011, they launched their health and medical sector, which is supposed to include laboratory design as well. And so do it again because Anschutz was being designed at that time frame was really not something that they were looking at very closely as that proceeded.
Let's see. What
The Labs 21 effort of the EPA,
Let's try this
the
and
annual
see
Labs 21
what gets
conference
us.
is now called the I2SL, or International Institute for Sustainable Laboratories Conference. And they were originating in 2004, again under the Green Buildings Initiative, to provide guidance on principles of sustainable laboratories, from design to engineering to operation. And so two of our speakers today, Tom Convery and Catherine Ramirez, if I got that right, are currently members of FRaBSA and recently presented at the Colorado chapter meeting in August on the Anschutz campus. So the confluence of design, engineering, and operations with respect to biosafety is what I'm hoping you can get some education on today. It's an important and timely topic. If you stay in this career field for any length of time, you will be involved in either a remodel of a laboratory space or new construction. And very often it's the remodels that get us into trouble as opposed to the new construction. But it can be challenging no matter what. And on the biosafety side of the world, our guidance documents have usually been the MBL from CDC, which is not prescriptive in most cases, and then NIH Office of Research Facilities, I think is what they call themselves, also has engineering and design guidelines out there that they use for the NIH campus and projects that can inform us in what we're doing as well on our own campuses. But again, none of this is prescriptive, and then as things change, we need to know what the architects and the engineers are saying in terms of containment measures. Usually we rely on ventilation to do that. And from the energy usage standpoint, that can be highly ineffective if you have 100% air in, 100% air out. And in this day and age, it impacts our carbon footprint and our environmental footprint. And the other piece of that sometimes overlooked is that we also influence the materials handling in our laboratories from the time materials are received through the waste disposal. And there's a lot of energy as well as water resources that go into those efforts. And one of the things that you may or may not know about is that Colorado is relooking at their water plan through 2050. They haven't finalized anything yet, but I think it will have a great deal of impact on the industrial and other commercial sectors, including hospitals and healthcare and research laboratories. So, moving on, our first speaker today is Sean Convery. He is a PE and a mechanical principal at Caterham and Associates in Denver, Colorado, a founding board member of the Colorado chapter of FRaBSA. His 20 years of mechanical design experience include energy-efficient mechanical systems for research labs and higher education campuses. Over the course of his career, he has gained expertise in sustainable lab design and to date has been involved in the design of over 65 lab projects. Many of them are biosafety level 3 and veterinary medicine laboratories, which have provided an opportunity to design unique systems such as effluent decontamination and tissue digesters, a topic near and dear to my heart. His recent projects include the Colorado State University Diagnostic Medicine Center Digester number 2, the CSU Bioengineering Building, which is LEED Gold, CU's Boulder's Biotechnology Building, I think that's the Smalley building? Yeah, LEED Platinum, and the Wyoming State Veterinary Laboratory. Convery is often invited to give presentations at conferences such as Rocky Mountain AAPA Conference, DBIA, I don't know that one, ASHRAE, and the annual I2SL conference, where he enjoys sharing best practices and lessons learned. Our second speaker today is Catherine Ramirez Aguilar. She manages the CU Green Labs program at the University of Colorado Boulder campus, a program she has been building and creating since 2009. She has a doctorate in analytical chemistry and 15 years of laboratory research experience within the fields of biochemistry, analytical chemistry, and organic chemistry. Through active participation in the I2SL community and annual conferences, Green Labs Planning Group, and the DOE Better Buildings Alliance, she regularly collaborates and shares ideas with colleagues across the nation at universities and federal agencies who care about efficiency and sustainability in lab environments. She is a member of the DOE BBA Higher Education Steering Committee and leads the I2SL University Alliance Group, which is presently exploring the topics of connecting sustainability to lab finances. We'll also have a short presentation from Ken Gao, I hope I said that correctly, and Eric Bratt from Merrick Incorporated. I don't have their bios, I apologize. And now, Sean.
Thank you. Can everybody hear me? So feel free to stop me as I go. Again, being a mechanical engineer, I don't always speak the same language as biosafety personnel. So if I say something that needs sort of clarification on, stop me, ask questions along the way, I'm fine with that. I like to use lessons learned from my projects and other projects to help demonstrate some best practices. So today we're going to talk about some things likely after lunch because there's going to be some fun discussion talk later on. I don't know if this one's
Did they change this on? We are just not cooperating today, are we? I'm going to make him change that. Well, here you go. I will get this. Well, we got that on. This is not working. Did it work before? Don't know. All right, we're working now. For whatever reason, it's working now. Now we're on to switching, so we'll see.
All right, so these are our learning objectives. I want to talk about process cooling and how we can use process cooling systems to save domestic water. And also, we'll talk about vacuum systems because that's often achieved by using tap water to create vacuums. Then I'll talk about wastewater treatment for BSL-3 labs. And then lastly is more of a solid waste, tissue waste process and adoption. First, we'll talk about domestic water use in labs. And this is where, the internet was wonderful to give me a bunch of pictures of things that I'm pretty sure you guys have seen in labs. An aspirator, for one, is a way to create a vacuum by running tap water through a venturi. Better picture of it is using tap water to run through this jet, this venturi jet, to pull a vacuum and pull gases out of an experiment, and then you're just discharging that to the drain. Another example is this type of apparatus that has not only a vacuum port that would typically go to an aspirator to pull a vacuum, but then using tap water to be used as a condenser. And yet another picture of tap water being used to create a vacuum for filtration process. So these are all little apparatuses that sit in labs that are using water constantly. I remember one of my first jobs at CSU, when we were adding on to the chemistry building, I went into the basement of chemistry, I looked at a glass pipe, and it was a 6-inch glass pipe, 3/4 full of clear, fresh water running down the drain constantly. It was just amazing how much domestic water was just being wasted for those types of processes. So why not put in a central vacuum pump system that is then piped to all the labs, and then you can have lab turrets to create that vacuum, so you don't have to use any domestic water to create your vacuum. Another big water waste are autoclaves. Autoclaves are used in labs, healthcare facilities, to sterilize your equipment, or to sterilize trash from BSL-3. This particular one was installed at CSU's first big BSL-3 lab. It's a big bulk autoclave. The closer picture is, this is the floor sink, which is about a 12 by 12 floor sink. You can see it's just constant dumping of water. This was during the idle phase. So the unit wasn't even running, it was just cooling the condensate that was fed around the jacket of the autoclave. This particular unit was using anywhere from 12 to 20 gallons per minute constantly. It was over 1 million gallons of water used per year for one piece of equipment. Newer autoclaves have water saver kits, and they also have heat exchangers, which I'll do a blow up here. So this heat exchanger is a plain heat exchanger using aluminum brazed together, and it takes the condensate off of the autoclave, runs it through the heat exchanger, and this pipe and this pipe are the supply and return water going backwards. These pipes are supplying the return process cooling water coming from the building's chilled water system. One big lesson learned on these types of heat exchangers, we had 2 projects at CSU where the heat exchangers were failing. The brazing material between the plates was cracking. Now, we don't know if it was caused from thermal shock or was it just poor manufacturing of the heat exchangers. But CSU is losing hundreds of gallons of propylene glycol down the drain. During this process, they were trying to find where's all our glycol going. Finally, we found the floor drain in this autoclave service room was pink. Okay, that's where our glycol's going. So I think they're still in battles with STERIS to try to figure out how to either fix those heat exchangers, or in the future will they create heat exchangers that work better. But that's a lesson learned you need to think about, because if you're going to start dumping a bunch of processed water down the drain that's chemically treated, now it might cost more than just dumping water down the drain. Another way to use process cooling is all your refrigeration purposes. So a lot of your labs have walk-in coolers, they have controlled environment rooms, growth chambers. All these things have the need to reject heat somewhere. And the best way to do it is through a water source. Rather than having an air-cooled condenser sit on top of your walk-in cooler that's just rejecting heat to the ambient air inside the building, it's a lot more efficient to transfer that energy to water that can then go into a chill water system, a campus distribution system that is much more efficient than the air side. So how that works from an engineer's perspective or a contractor's perspective is This is a one-line diagram, a flow diagram of chilled water. So, for example, this pipe comes into the building from a district loop out in the dirt. It comes in and it goes over and feeds a chilled water system that serves air conditioning purposes in the building. When we simply take off that chilled water system and go through a heat exchanger, this process system only needs roughly 60, 65 degree water. This water is coming in at 42 degrees. So we use the heat exchanger to not only control that 65 degrees, but to buffer it so you don't send too cold water to your equipment. We go from that heat exchanger through some pumps up the building to a controlled environment room, to an autoclave, and to whatever other equipment can accept it. You know, the ice maker can accept process cooling. Some of your lab equipment can accept it. Laser lamps, they want it. So that's what we would end up taking it to. Now, the more efficient way to do it, this is a little more confusing diagram. I apologize. It's a control diagram, but the same thing. It's using a district cooling piping from outside through a heat exchanger. So for the process side, what we're doing is we're pulling the return water. So it's already been used for the air conditioning process through this first heat exchanger. So it's risen that temperature from 42 to 56 degrees. Normally you send that 56 degree back to the campus loop, back to the chillers. But what we're doing is we're taking that 56 degree water and we're using it again. We're going to another heat exchanger, and then we're going to rise that by another 10 degrees and try to send 66 degree water back to the campus. Campus central cooling plants and loops have historically had issues with what's called low delta T syndrome, where the chiller plant wants to create a 15 degree temperature differential for energy purposes. But all the buildings that they're serving have old equipment, old air handling equipment that can only do a 10 degree differential. So places like CSU are really looking for new buildings to increase that delta T across that building to help the whole campus have a better energy profile. So what's a heat exchanger? Well, this is a typical HVAC heat exchanger. This is what's called a flat plate heat exchanger. And the way that works is these are aluminum plates, very thin. These things are very thin, put together by gaskets. And every other plate sends either the cold fluid or the hot fluid crossing against each other. It creates a very good heat exchange surface and allows you to get within typically 3 degrees between the two fluid streams. If you spend more money and more plates and make this really big, you can get close to a 1 degree approach between these two fluid streams. Let's say you don't have a district cooling system or a big chiller plant in your building, you have a smaller building, you can implement what's called a process cooling tower, where it's basically just exchanging energy with the air. These are 2 big fans blowing air across a coil, and that coil is the process water going to your equipment. This one is a fluid cooler, so it actually sprays water up here to do evaporation across the closed loop cooling coil to get more efficient heat exchange.
It stopped. That was me that made it stop. Sorry about that. There you go. Should have it back.
So to back up, the biggest lesson learned when it comes to process cooling, and we learned it in sheet learning. I just dealt with this yesterday with one of my engineers, is laboratory equipment manufacturers have been so used to using tap water that's got high pressure, 80 psi in buildings, and they don't care what the return pressure because they're just going to the drain. So for us engineers, we need to know how much pressure differential your laboratory piece of equipment requires. Because for us to size the pumps, if you go back to here, for me to size this pump, over here, I need to know flow rate and I need to know pressure drop. If they say, well, I just need 80 psi, well, that's what they get from the tap water. We need to know incoming and exiting pressure so that we can actually size this pump. What typically happens, if they don't know it, they give us the wrong information or we guess, and then it's wrong, then the equipment doesn't work. Or it can't cool to its specs. So whatever this group can do to help that, switch over to liquid waste. This is focusing on BSL-3 containment facility. Now, CDC and NIH don't specify that you have to do absolute decontamination. That is more of a risk analysis. So not every BSL-3 lab I've done has a decontamination system. So you have to work with your biosafety officers and your risk assessment team if you develop a new BSL-3 lab and figure out what kind of decontamination system do we need. So for a lab we did at CSU, we had 3 sinks that was in 3 separate rooms for mosquito breeding. And they were concerned about the larvae making it down its way down the sink, and it could still be live. So we took those 3 sinks and put them into what we call a kill tank. This was all developed by ourselves. We didn't go to a manufacturer. I kind of call it the poor boy approach to a absolute decontamination system. The process is the waste comes from the sinks into the tank. We have a motorized isolation valve here on the inlet, and a motorized isolation valve on the outlet. We have a steam system that comes in and feeds a coil, and the condensate goes out. This is all controlled through the general building automation system that the controls contractor is used for all the HVAC controls. When the level sensor measured that it was high enough, it would close the inlet valve and then send a signal up to the researchers in the lab, a red light saying, tank's full, stop what you're doing. It only takes 3 minutes to kill whatever was in this tank. You had to raise that temperature up to, I think it was 150 or 160 degrees for 3 minutes. And then it was done. And then before we sent it down to the city waste, we had to bring that temperature down to 140 degrees. So in this one, we only allowed it to get up to about 75% full, do the kill, and then let the cold water come in and flood the rest of the tank to get it back down to 140 degrees. Then we're able to release the water, and then the light will turn on the lab, and then okay to start dumping water down the drain again. You can see how complicated it is. There's always going to be a lesson learned. There's always something go wrong. So the thing that went wrong on this was this vent pipe was a copper pipe. It went up to the interstitial space. And on this project, we allowed PVC piping for the rest of the vent piping in the building. And because that vent piping was exposed in the BSL-3, because previous projects was copper, and copper inhibits the activity of VHP for decoms. So on that project, we said all PVC. Well, we connected the copper pipe to a PVC pipe up in the interstitial space. We controlled the honey wire during commissioning. We boiled the water, and 200 degree vapor went up the pipe, got to the PVC, warped off the pipe, and then hit the interstitial space. And that had to be replaced with copper. So that was a big lesson learned. That vent pipe should have been a separate pipe out of the roof, and that would never been an issue. Here's a picture of the final installation prior to, I think these pipes were insulated at the end, but it's just a real simple tank with an inlet and outlet pipe, vent pipe coming up top. This is the steam heat exchange pipe going in. Then if you got a lot of money, you can call up Gary Schmidt. I'm sure you guys have met him. And that's one of the decontamination system. PRI is probably one of the more renowned companies to provide this. This is a diagram of the EDS unit we put in at the UW Med lab, the BSL-3 lab, that we took all of the drainage from that lab to the system. The way this works is you have a collection tank that gathers all the water from the lab. And then you have a treatment tank. So this is always acting as a buffer so that the treatment tank can do its kill process and you never have to turn the water off upstairs. You just let this tank keep collecting. After the treatment's done, this tank then discharges to a cooling tank where they introduce the heat exchange or domestic water to cool it down, and then that's discarded. All of the fluid transfer between this tank and this tank is used just done by compressed air. There's no pumps or anything. It's just high pressure air pushing the fluid between the tanks. This is what it looks like. And to give you an idea of scale, I think the top of this is about 90 feet. This space is about 15 feet tall floor to ceiling. So it's a pretty sizable unit. So find the lessons learned. So let me point out, so this is a collection tank. This is the kill tank. And then this is the cool down tank. First lesson learned, another venting issue. The vent is very hot coming off the kill tank. The contractor was good enough to insulate that pipe until he penetrated the floor above. And then he ran that pipe in a block wall up to the attic where he insulated again. Well, that block wall is now discolored and it's hot to the touch because he didn't insulate that pipe. So now we get to relocate that pipe in other routes so we insulate the whole way. It's complicated. You got to go through commissioning. You got to go through recommissioning. I mean, one of the lessons learned on this gut is that it's been around for a couple of years, but there's not been a recommissioning process. But CEC requires these DSL 3s to be recommissioned. And I would vote that something this complicated, you got to recommission that anytime you recommission the line. You should get a maintenance contract. You shouldn't rely on your maintenance staff trying to figure out what the dials and what the valves are doing. You should get a maintenance contract that brings in PRI or one of their authorized dealers to service this on a regular basis. And then lastly is, this isn't really set up in solid waste. So if you're dumping solid down the drain, you got to be careful because you're using compressed air to push liquids between tanks. So if there's solid getting down there, that could, create a blockage. Just another picture of it. All right, now the fun one. Good thing you guys enjoy your lunch. So for facilities that just have rooms to deal with, this is a picture of a building at UW, University of Wyoming. We were looking at this because of some lessons learned, and they were looking to do a project to remedy some of those lessons learned. It's a small incinerator, probably 5 feet tall by 3 feet wide, not very big. It's old, it's probably 1960s vintage. So what happened was they had an HVAC upgrade for the building. They put on the rooftop air handling units, new VAV valves, a bunch of stuff, and they actually served the vivarium on that top floor. But what they didn't think about was this existing incinerator and the stack sticking to the roof. So after that project was done, they started getting indoor air quality complaints because the incinerator smoke was getting sucked back into the air intakes. So what they do, when they fix the stack, they put a control relay to kill the incinerator anytime the wind direction was going to push the wind to the air intake. That was poor researchers. He goes and puts a load of mice in there, starts the kill process, wind shifts, the automatic control shut it down, he goes to open it and fills the room with smoke. They're asking, hey, can we put an exhaust in here? And we're trying to figure out what we can get help them out. But it's simple little things that tend to create a really big problem here. Now you could also go with a really large incinerator. This one can handle entire farmlands, cattle, that sort of thing. This is at the University of Wyoming Vet Lab. The biggest lesson learned here is, and I apologize, I'm just repeating what my boss said, because I wasn't involved at that time, but we got called up there because the room was so hot. So there's a room up here for this minute. There's a room where you bring the air and you drop this carpet down into the incinerator. Well, the room was so hot that the light fixtures were warping. And of course, they thought it was a mechanical engineer's fault, even though we didn't specify this thing, nor did we build it or anything. Well, they didn't insulate a single piece of it. This is one of these bare steel just radiating the heat from that blast furnace into the building. So, big lesson learned is make sure your manufacturers are insulating their products, whether it's in the factory or when it shows up on site. Somebody needs to insulate that, insulate this, insulate the stack until it penetrates the roof. And then we still had to go and put additional ventilation into that room to get enough air movement to get that heat out of it. this is what their outside looks like with the stack going up. The other lesson learned that could have been a problem here. Luckily, the stack is really tall, but on that project, they didn't do a wind analysis of dispersion study. I highly recommend a dispersion study on every lab project that's coming out of the ground, so that you don't affect people on the roof, you don't affect your air intakes, other buildings. This one's out in the middle of nowhere, so there's no other buildings around it, but from Hampton campus, CSU, you guys got all these other neighboring buildings. Do the wind dispersion analysis. It's not as expensive as it sounds, probably in the range of $20,000 to $50,000. But when you're doing a $50 million building, just do it and make sure that no one's going to come to you 2 years later and say, I'm sick because of those exhaust stacks. All right, my favorite. So there's competing theories of science when it gets to the chronic wasting disease and the prions that are associated with it. My understanding is years ago, CSU scientists learned that incineration doesn't necessarily kill that protein all the way. And so they implemented tissue digesters. This is a nice screenshot from PRI. They're never this clean. But it shows the different options you have. You got horizontal digesters, you got these vertical digesters. You get really big ones, which we'll get into a little further, where the waste can go down into a container that's on wheels and be disposed of. Some of them are just piped to the drain, and they go to the sanitary system. The biggest issue and lesson learned people have with these is the wastewater department just doesn't want that waste coming to the facility. CSU's first attempt at this, City of Fort Collins shut them down within months of dumping it in the drain. And that's when they had to go to a solid removal system. 2 years ago, we actually removed the digester at UCD and issued R1 building because it's a wastewater system. Where wastewater department wouldn't let them use it anymore. So you had this brand new shiny machine that probably cost $500,000. We had to get rid of it, put it in a freezer so they could store their mice until they sent it off to incineration. So this picture is our recent installed 4,000-pound tissue digester at CSU. Behind it is the ugly stepchild out back. This was installed initially at the vet hospital before we built the Diagnostic Medicine Center. And then we built the Benson Center to accept the old digester and the new one. And then after we got the building done, the company who went out of business that moved this installed it with really shoddy work. The unit kind of ran well for a while, but they've had problems with it ongoing for the longest time. A couple of the lessons learned from that older unit is the size of these openings. There was 2 openings of this size, roughly 2 foot diameter. CSU is dealing with whole cows, horses. They're dealing with large animals. So they had to cut up the animal into small pieces in the buckets, use the crane rail system to come over and lift the bucket, and then they've got guys launching this bucket into the digester. So it became pretty disgusting and messy in there. There was indoor air quality issues. So this is always a fun story to talk about. We get called up there as the engineering director to say, your carbon filter, your air handling system isn't working, this is terrible, it stinks in this building. Okay, so we go in there, it smells great, one your conference show, and just out of the blue, we smell the digester smell. And we're like, oh, there it is, let's go find out what's coming from. We go downstairs, there's roll-up doors wide open, there's a pumping truck outside, pumping water out of there, spilling it onto the ground, all the odor from the digester rooms coming out the roll-up door. And we had this thing dialed in to be a negative pressure room, but as soon as you open up the roll-up door, you're exposed to the whole world. So it became a lesson learned about protocol. The people that operate that facility had to change their protocol. Don't use a roll-up door for smoke break. Keep the door closed. one of the biggest things was the bins that I showed you before. These bins down here. So when the waste comes out of the digester, it's still in kind of a molten liquid form. It's off gassing. It's cooling down. It takes hours for this material to cool down. And when it's doing that, that off gassing smell is horrible. I can't explain how horrible it is. So the protocol became, you don't take that bin outside until it's hardened. Once it's hardened, there's no odors, it's inert, it's fine. But when the building was designed, the architect had planned on the protocol being to take that bin up the lift outside, around the corner to a ventilated closet. Well, that quickly became useless because we couldn't let the bins go out of space until it was fully cooled off. Give you a better scale, the guy's at least 6 feet tall. It's a really big machine. I highly recommend this type of design with the full circle lid being lifted up so you can get the whole animal in here. I highly recommend the overhead crane rail. You almost have to do that when you're dealing with large animals. Talking to the guy that's running it now, they can put a whole cow into this machine without even having to cut it out anymore. So they're pretty happy with that installation. And this lid is motorized. You see all this funny stuff back here. Watching this thing lift up in the air is really cool. Now I got to figure out how to run this wheel.
Well, we're going to do Assassin's Creed.
How do we get back to the slideshow? There's a little bar down there. On the screen.
Somewhere around here. Whoops. This.
What's in the
Oops. So I'm supposed to be able to somewhere, huh? Well, we'll go this way. My just so.
Oh, we're not showing them the aliens.
You gotta imagine.
All right, we're gonna try. Are we?
So anyway, it's a big paddle wheel that surrounds the circumference of the chamber, and it just rotates. It starts out when everything's not broken down, it's really slow. But they sped it up for us to maximum speed to really see this thing splashing the water out. And their design is great with this because that paddle wheel goes down and it scrapes the bottom of the tank. And the tank has an outlet on the bottom, whereas the previous design was long and horizontal. The drain was in the middle, there was nothing scraping it, so to empty it, they had to get a rod, open the valve, and start hammering the drain opening to get the fluid to flow.
All right, so we're not getting anything, right? All right. But it's kind of cool. If you could see it up here, it's really kind of cool. If I could just get it for you guys to see it.
Really?
So the old digester, it would take them about 4 days to run a batch.
Oh, wow.
This one does it in less than a day. So I think it's 12 to 16 hours for getting 4,000 pounds of tissue digested.
What happens to the material after it's digested?
It goes away. So they wheel it all outside and they have a truck come pick it up every so often.
I read somewhere that Emory is doing small animal carcass composting. And so is the digester only for the items that have biohazardous considerations that are going to be done, or are they doing it for everything?
I think Bob can answer
No, it's not.
Just kind of like yes.
Whoops. Sorry about that. I didn't mean to start that again.
Okay, I'll finish that. This services all the tissue from the veterinary teaching hospital that doesn't survive, as well as the whole veterinary diagnostic laboratory. So any carcasses, any tissue, anything that needs disposed in more night for some reason, some of it is not infectious disease, but quite a bit of it is. So it all goes through the diagnostic. And it is effective against prions, so that material definitely comes through the diagnostic. This basically is pretty much of a huge incinerator, if you want to picture it that way. And about 20 years ago and further back than that, actually maybe 15 years ago,
I can figure out. Sorry about that.
Now, they pretty much don't do that at all. They just gradually got down to where have to take care of the tissue ourselves. And like Sean said, it could be it's multiple horses, multiple cattle, all the way down to the fence every day, every day. And so it's a huge load of tissue that's digested that breaks it down. Prion, for example, is about 165 amino acids, that chain of the prion, but it breaks all this down. It breaks the bonds in the proteins down to monomers, tumors, trimers, on up to maybe temers.
How is it breaking it down? Is it heat?
Oh, I'm sorry. I can describe the process. I can describe the process. So, the digester. It's not going to show. I'm not going to show a picture, but we bring high pressure steam to the machine. It goes through a heat exchanger and heats up oil. That oil is then circulated around the chamber, inside the stainless steel chamber, to heat the fluid and material inside. Once that has broken down the material enough to be fluid, they inject hydroxide. So it's a caustic, acidic chemical. They break it down because it's basic, it's high pH. Yeah, very high. And then that caustic material is added near the end of the cycle to break it all the way down. And then it goes through a cooling process, a dehydration process to try to extract as much of the moisture out of it before then it's finished and you go into the canisters.
So there are two issues with the effluent. One was, like Sean said, the protein load. The utilities department of the city of Fort Collins, where the water treatment plant is about 4.5 miles from this. They told us that they could tell the instant how long this was being done. After it went through 4.5 miles and mixed or not with all the other sewage that was coming through the sanitary sewer, then Fort Collins in that 4.5 mile run. So it really doesn't mix much. The other thing was that the pH would be 12, 13, something like that. You have to get it down. I don't remember what the requirement was, but yes, you would have to lower that to whatever the pH was. It seems like it was 11, might have been 10. It had to be at that level before we discharge it. But we could discharge it, but the cost was prohibitive because they charged us for the biomass that was being discharged. Because they said, you know, they just couldn't, the sewage treatment system wasn't built to handle a huge bolus of that all at one time. They said it was like 300 to 400 at least. It seemed like it was 350 to 400 homes flushing their toilets all in one time. That was what the biomass was.
I'm sorry, can I ask one more question? So you're not doing all your animals on campus through the digester. There must be other animals that are at CSU that don't go to the digester at the end of life.
So the question is, are we doing all the animals that are on campus, all the research as well as clinical diagnostic? The answer is no. This is specifically for the veterinary clinics and the veterinary diagnostic laboratory. So other animals, we've got one doing on campus where there's a lot of large animal research. Those animals all go through the incinerator. The other animals, lab animals are autoclaved and they may be going into the normal trash. So, like Sean said, the effluent or the liquid is evaporated off to a certain extent. It's built the evaporation or needed to evaporate some of the liquid, but then it's evaporated down to what would be a gel, and then that's allowed to solidify. Then that goes to landfill.
So, to talk a little bit more about what we experienced at Antec, is that the call wastewater didn't make us permit it when it was first installed. And then they had a change in leadership. Okay. So what happened with Antec was that when we installed our tissue digester around 2004, I think it was put in service. At that time, the city of Aurora and Metro Wastewater did not require us to permit it as pre-treatment or any of those issues that would go along with it. We had it set up so that it was neutralized before it went into the sanitary sewer system. At least that was at the time. They came back and did an inspection for Metro Wastewater of the entire Antec campus. So the hospitals as well as the research campus in 2008, and that lasted about 2.5 years until they had gathered all the information they wanted, and then they came back and said, because they had a change in administration, but they did not like this technology. They did not, as far as I know, have any data indicating that there was a bolus of protein, and we don't certainly have the large animals getting it. So the largest animals that were going to it were swine at the time, and goats, not goats, I'm sorry, sheep. There were some indications that it was being discharged without the pH and the temperature being completely within their parameters. And they mentioned that there was an increase in DOD, but again, they didn't necessarily come back and say it's like having 400 grams plus the liquid all at once. And it was more of a political decision because they had heard of other locations in the country where they were talking about using it as a crematory service for human remains. And they did not want to go down that slippery slope in the state of Colorado by allowing animal remains. And so I think it cost $500,000 to pull it out and replace it with research. But it just, you have to know what your wastewater district is going to be able to deal with, and then they have the final say. There's no appeals process once they make a decision.
On that same project, Answers was required to stop sending the bedding material from the librarian down the drain. They had these what's called carvels, these huge garbage disposals that was taking all the waste from the librarian and just grind it and send it down the drain. So on that same project, we had to put this very fancy vacuum system that was sucking the bedding material out of going into the compactor.
So the other thing to remember, Kathy, is when you say biohazardous, it doesn't just mean infectious. under the NIH guidelines, if you're working with transgenic animals, those cannot be released in the environment. You have to treat them in some manner. You can't go to landfill and hold carcasses, and they cannot go to, for example, a raptor feeding zone, because that's considered release from the environment. So it's not just in fact.
So the other point, I just remember too, from a city of Fort Collins standpoint, we debated this back and forth. We had some pretty meaningful discussions here. But the bottom line was, they said, if we have a brewery, which there are quite a few of those, that has a spill, and they spill thousands of gallons of material that also would require, or that would also be a really huge DOE biological oxygen event that would put the treatment plant in the same position as what our dumps are putting into. We would charge them the same for that spill as what we're charging we did on your cut. So the precedent is already there, and it's not going to be something
I just want to add one thing. So another alternative to both the digester and regulated installation, the non-regulated installation, is most commonly would be to think about a pet food plant. So if you have good internal practices for segregation of waste, carcass waste, where you can segregate out basically a clean animal, right, that's never had anything put in it, or may have had something put in it, but nothing different than you put in the pet. You can use a local crematorium, enter into an agreement with them, and send tissue carcass that way. And Friendship Medical is being utilized in local crematorium. It's actually our largest carcass waste stream. Either nothing's been put in the animal, or you might have a therapeutic or analgesic, or anything that you put in the pet. So that's another avenue that we've been able to take advantage of, because we lost the digester, rather than create a bigger carbon footprint, which is what you're interested in shipping all these carcasses to Fargo to a regulated incinerator. We decided to stay local, near pet food.
Any other questions? All right, thanks.
They were at one point.
Around it.
So they email you
At one point they couldn't, but then they could, and I haven't heard back from them since then. So we'll see what happens. Yeah. Huh?
This just pops off, right? So you can flip it.
I would think so. We're doing water conservation, right?
Getting the presentation up. Yes, does it seem reasonable? I know I read this, that Emory was composting small animal carcasses. Does that seem like something that is reasonable in your mind? Yeah.
So, well, I don't know the specifics of Emory, but you have to remember when it comes to regulated medical waste, we have 50 different states with 50 different laws. So each jurisdiction within the state to make their own rules. So in Colorado, because the landfills are owned by they can make their rules more restrictive than what the county or the state says.
Kathy, can I get your presentation again? It did not like it. Sorry.
I'm thinking
the rules in the city of Atlanta, the harder they're moving the waste out in the Georgia countryside,